Hi there and a very big welcome to the channel. My name is Ferguson Mangoma, Cambridge Advanced Level Mathematics here. In this video, I would like to show you how to find the eigenvalues of a matrix. Obviously, our first port of call is a definition. What is an eigenvalue? Well, we say that lambda is an eigenvalue of a matrix A if the following equation holds. The matrix A multiplied by a vector x is equal to lambda, the scalar, multiplied by vector x. Now, the equation is saying the scalar lambda is an eigenvalue of the matrix A if A multiplied by x, vector x, is equal to lambda multiplied by the vector x. The vector x is called an eigenvector corresponding to the eigenvalue lambda. So let's book this down. Our lambda is called an eigenvalue of the matrix A. The vector x is called an eigenvector corresponding to our eigenvalue lambda. Now, the identity matrix, when you're dealing with matrices, performs exactly the same function that the number 1 performs in ordinary arithmetic. If you multiply 30 by 1, you get 30. You multiply any number, 150 by 1, you get 150. 200 million by 1, you get 200 million. So the identity matrix performs exactly the same thing on vectors and matrices. You multiply a vector by an identity matrix, you get the same vector. You multiply a matrix by the identity matrix, you get the same matrix. So we can play around with this part here and say lambda x is equal to lambda multiplied by the identity matrix multiplied by our vector A. Nothing changes because vector x multiplied by the identity matrix remains the same. Now we can take this here and plug it over here. So we can now write Ax is equal to lambda multiplied by our identity matrix I multiplied by our vector x. Let's take everything to the left-hand side. We now have Ax minus lambda I x is now equal to 0 because everybody has gone to the other side. We can factorize this, factor out our vector x and write A minus lambda I brackets vector x is equal to 0. Now this is a matrix equation saying the matrix inside, because what is inside here is just another matrix. It's matrix A minus the identity matrix multiplied by lambda, which is just another matrix. We could call it B or we could call it matrix C, but it's just a matrix inside the brackets. Now, this matrix equation, it says this matrix here multiplied by x gives us 0. The only way that this equation can have non-trivial solutions is when the determinant of the matrix inside the brackets is equal to 0. Let's repeat this important equation. If this equation is to have non-trivial solutions, in other words, the solution x is equal to 0, then the matrix inside the bracket must have its determinant equal to 0. So let's write down the condition here. This says the determinant of the matrix A minus lambda I is equal to 0. This equation we have written here is called the characteristic equation of matrix A. So it's the characteristic characteristic equation for our matrix A. Now, we have two important things here. Let's remember this here. And let's remember our characteristic equation. Now let's see where the rubber meets the road. Let's take a specific example and see how we can use all this information we got so far. Now, supposing our matrix A is equal to, let's say 4 minus 2, 1, 1. First of all, let's set up our characteristic equation. The characteristic equation is the determinant, says the determinant of matrix A, 4 minus 2, 1, 1, minus the identity. Of course, this identity is a 2 by 2 identity. So we multiply that by lambda. It becomes lambda 0, 0, lambda. This is a determinant, and it should be equal to 0 for this to have non-trivial solution. So this is now our characteristic equation. We can, of course, simplify things because this matrix minus that matrix gives us 4 minus lambda minus 2 minus 0, which is minus 2. 1 minus 0, it's 1. 1 minus lambda gives us minus 1 minus lambda. And this is the new determinant. And it's always equal to 0, our characteristic equation. Now, let's expand the determinant. So this implies that, remember, when you expand your determinant, it's the product of the elements in the main diagonal minus the product of the elements in the other diagonal. So it's this multiplied by that, which is 4 minus lambda, brackets, 1 minus lambda, 1 times minus 2 is minus 2. Minus 2, there is supposed to be a minus here, and then it becomes a plus, so it becomes 2. And this is equal to 0. We can expand our brackets here and write 4 times 1 is 4, minus 4 lambda, minus lambda, plus lambda squared, plus these two here. We simplify. This is lambda squared. 4 minus 1, that gives us minus 5 lambda. 4 plus 2 here, that gives us 6. Let's factorize this. This gives us factors of course, here, sorry. Here we do have we're going to have our lambda here and our lambda here. Factors of 6 subtracting to minus 5, it gives us 3 and a 2, and both must be negative. So this is equal to 0, which means, of course, that lambda is equal to 2 or lambda is equal to 3. So we have lambda is equal to 2 or lambda is equal to 3. These are the two eigenvalues of the matrix A. First of all, you must set up your characteristic equation, which is this equation here. Then you expand your determinant, which we have simplified this to that. You expand your determinant, you get to that, then factorize if you can, you end up here, and then find the solution. The solution of lambda gives you the two eigenvalues of our matrix A. In our next video, we are going to find out how we can then find the corresponding eigenvectors, the eigenvectors corresponding to these eigenvalues. Till we see you, bye-bye.